Okay, so we're looking at the second page as a separate video. That way it doesn't take me forever to load onto YouTube. So let's take a look at this one. This time they gave us a rational function where the numerator was a second-degree polynomial and the denominator was a second-degree polynomial, and you're being asked to find the domain and the range. Now remember, the domain, the easiest way to find the domain is to find the vertical asymptotes. And the way we're going to find the horizontal, or the range, is to find the horizontal asymptotes. Now right off the bat we can find the horizontal asymptotes without doing too much work. The horizontal asymptotes, because the degrees are the same, just like it was on the first page, is going to be the ratio of the leading coefficients. And so that's going to be 3 over 1. So our horizontal asymptote is where y is equal to 3 over 1, or 3. And so we can say that the range of the function is the set of y such that y is real, but that y does not equal to 3. Now, the vertical asymptote is where the denominator is 0. So what we're going to do is we're going to go on ahead and we are going to set x squared plus 10 is equal to 0. And just like we were Algebra 1 students, we would subtract 10 from both sides, and we would get that x squared is equal to negative 10. Now to solve for x, we would actually have to take the square root of negative 10. I'm going to do this in pencil because you really can't take the square root of a negative number. So you're going to take the square root of negative 10. Now the thing is, you really can't do that. So there is no real number that would cause a vertical asymptote to exist. And so therefore, since there is no real number that would have the vertical asymptote existing, we would say that the vertical asymptote is empty, or we would say that it is null. And so therefore, the domain is just simply that x is the set of real numbers. And so unlike the range, which has an exception at 3, in this case, the range, or the domain, is just any real number at all. Now, on to numbers 14 and 15. There was a little typo here. For some reason, the y equals didn't show up on either of these. I don't know why, but that's all right. And now you're being asked to translate it 3 units to the left and 4 units up. So what we're going to do is we're going to take y is equal to 1 over x plus 4, and then we're going to translate it, and I'm going to use my pretty red pen to do that, 4 units up, so that means we have an outsider of 4, and 3 units to the left. Now the thing about translating to the left, and y'all can't see that right now, here we go. The thing about translating to the left is we remember that insiders lie. So you would think it would be minus 3, but actually it's plus 3s because your insiders lie. And now you're going to combine your like terms, and so that gives you the function that y is equal to 1 over x plus 7 plus the constant 4. Now immediately that tells you that you have a horizontal asymptote. You have 0 here because 1 has a degree of 0 and x has a degree of 1, but then you add it 4. So you actually have a horizontal asymptote of y is equal to 4, and you have a vertical asymptote of x is equal to, now remember, insiders lie, so it's not positive 7, it's negative 7. Now, so your domain and your range, the sets, is where the asymptote is not. So, the domain of the translated function is the, again, it's the set of x such that x is real, but x will not equal negative 7. The range of the translated function is that the set of y is real, but that y does not equal to 4. And that's it. All you have to do is find the asymptotes. Now, 16 and 17 are a bit of an interesting challenge. So let me zoom out so you can see the number line, and actually translating it to the number line is going to be the interesting part. Now, on your paper you should be able to see the function. And I'm just going to graph it on my handy dandy calculator to give you an idea. Actually, I'll pull the cable off. One of these days I'm going to figure out how to direct feed calculator imagery into the YouTube, but not today. So, we're going to turn the calculator on, and you're going to put your numerator in parentheses. So we're just going to say, okay, x plus 2 divided by parentheses x minus 1. You have to put the parentheses, otherwise things are not going to look right. So, we are looking, because here's our y equals, and this is f of x, so actually let's go on ahead and call this the f of x to be consistent, and this is f of x as well. So we are looking for where f of x is greater than 0. Now in this case, finding where it's greater than 0 is trivial because 0 is the horizontal asymptote, but it's also the x-axis. So let's go on ahead and take a look at the graph. Now, I'm going to zoom in using the document camera instead of using the calculator for a moment. Now, if you look closely, you will see that the rational function is above the x-axis until you get to a certain point. At a certain point, it intersects. Now, we're going to use our table to find that certain point. Then it goes down, then it goes all the way down to negative infinity, and just like an 8-bit gaming glitch, once you fall out the bottom, you wind up at the top. Asymptotes are a little bit like that. Then you're above the axis from there all the way to infinity. So, you need to find your asymptote, and you need to find your point of intersection. Now, the way you're going to do that is you're going to look at the table. Your asymptote is where the error is. Now, remember, you were looking for where it intersects with 0, and nicely enough, it intersects with 0 at negative 2. So you have two critical points, one at the asymptote and one at negative 2. So, the asymptote is going to be at positive 1. So I'm just going to put a positive 1 here. And then I'm going to put a 0 here, negative 1, negative 2. Now, I'm not actually going to put 0 there because that would make it all jumbled. Now, because this inequality is where it is greater than or equal to 0, I actually include the point at negative 2 where they intersect. If it was a exclusive inequality like this one here, I would have an open dot, and I'm going to demonstrate that to you shortly. Going back to my table, negative 3 is greater than 0, as is negative 4. So, everything less than negative 2 fits the conditions put forward in the inequality. Now, you also have a very small place between the 0 and the error, where the terms are less than 0, and that's okay. But then, once you get past x is equal to 2, once you get past x is equal to 1, things start getting positive. So you have the open dot at the error because you're never defined at the error. You're never defined at the asymptote, and then it goes this way. Now, and you didn't see me draw that, so I'm going to draw it for you again. So you have the open dot here, and then you realize you're going to the right. Now, there are two ways to illustrate this, and you need to be familiar with both. One is what I call the unidirectional interval, and the other is the true interval. Interval literally means between two values. So, in this part here, don't think of it as going from negative 2 to negative infinity. You actually read your intervals from left to the right. And so this is actually the interval of negative infinity is less than x, which is less than or equal to 2, or to negative 2. Now, the reason you are not defined at infinity is you never are. Now, the abbreviated way of writing it is simply that x is less than or equal to negative 2, because it goes without saying that x is less than negative infinity. Now, the other interval is that you start at 1, and that x is greater than 1, and that 1 is less than x, which is less than infinity. Of course, it goes without saying that x is less than infinity, so very often they write it as x is instead greater than 1. These lower terms is how you learned it in elementary or in Algebra 1. These higher terms is how we should come to understand these as we get ready to think in terms of interval notation. So now we're going to do a similar process with the second one. It's the same left-hand side, except now we are comparing it to 2, and we're looking for where it is less than or equal to 2. So the easiest way to do that is to go back to your calculator, and we are going to just go on ahead and plug in 2 for your second y. Now this will create a horizontal line because 2 is a constant function. Now, this is where you as thinking human beings look at the thing and say, wait, I am looking for where the function is less than 2. So that means I am looking for the parts of the graph that are below the horizontal line. Now, if you look right here, my entire curve until I get to the asymptote is below the horizontal line. After the asymptote, I'm above the horizontal line until I intersect it. So once again, I'm looking for the asymptote, and I'm looking for the point of intersection. To find the intersection, I'm going to go back to the table. So I look and I find that where x is equal to 4, y is equal to 2. So my two critical points are where x is equal to 4 and where x is equal to 1. So we may as well go on ahead and count that out. I like not starting at the very end, but just starting here at 4, and we have 3, 2, and 1. 1 is where our asymptote is, so we know that it's going to be open. And we also know that we're going to be open at this point because we are being asked where it is less than, not equal to. So in this case, we'll have open points on both. Then we will go back to our graph, and we look and we behold that the curve is less than until we get to the asymptote. So that means everything to the left of the asymptote is less than 2. And I look again and I see that everything to the right of the intersection point is also less than 2. Once again, you have the option of using, shall we say, true intervals or baby intervals. In this case, I say that negative infinity is less than x is less than 1, and 4 is less than x is less than infinity. To pare that down, I can say that x is less than 1 and that x is greater than 4. But these are true intervals, these are not. These are abbreviated intervals on the bottom. Now, the last one is a little bit more tasty insofar as instead of giving you the function before, you are going to have to write a new function. But the principle is fundamentally the same. You will go back to your calculator and change it up. Here you have a different constant function and a different rational function. So, I'm going to clear both of these off. And so you have that x plus 4 is being divided by x. And you are comparing it to where y is equal to negative 1. So, once again, we graph it. We see a rational function, another rational function, and then a constant line. This you have to read carefully because you are asking yourself where the rational function is greater, which means we are only concerning ourselves with the parts of the graph that are above the horizontal line. And so, once again, we need to find the asymptote and we need to find the point of intersection. To do that, once again, we go to the table. So, we have found our asymptote where we have the error at x is equal to 0. And where x is equal to 2, we find that the two y values are the same, so that's the point of intersection. So, we have critical points of 0 and negative 2. 0 for the error, negative 2 for the intersection. So let's go on ahead and put a 0 here and a negative 2 here. And the computer was thinking about it and almost went to sleep on me. I hate it when that happens. It's even more vexatious when my students fall asleep on me. Now, we go back to the graph, and we find that everything to the right of the everything to the right of the asymptote is above the line, which is what we're looking for. Once again, these are exclusive inequalities, so both of the dots should be open. So everything to the right of the asymptote is above, and everything between the point of intersection and the asymptote is below. Everything to the left of the point of intersection is also above the line. And so, because of that, let me zoom out so you can see the picture in its totality. You draw the line this way. Once again, just like before, you go from negative infinity is your x value until you get to the negative 2, which is your first critical point, and then you go from 0 to infinity, or more abbreviated, x is less than negative 2, and x is greater than 0. And that is how you deal with those number line problems, which are pretty gnarly. Now, 19, 20, and 21 are a bit of a challenge insofar as the numbers are small, and so I am going to use separate sheets of paper, and I will just write them out in longhand. So, let's start with number 19. You have x over x minus 3 plus 1 over 3 is equal to 1. The first thing you want to do when you are dealing with a rational function is you want to cancel the denominators. The way you cancel the denominator is by multiplying by the common denominator. In this case, the common denominator is we are going to multiply both sides by 3 times x minus 3. And what you do to the left, you have to do to the right. Now, what happens is we have then that you have x times 3 times x minus 3 over x minus 3 plus 1 times 3 times x minus 3 over 3 is equal to 1 times 3 times x minus 3. Well, of course, 1 times 3 is trivial. And the 3's cancel here, leaving you with x minus 3. Here, the x minus 3's cancel, leaving you with 3x. And you say that this is equal to 3 times x minus 3, which is 3x minus 9. You combine your like terms. You have 4x minus 3 is equal to 3x minus 9. You subtract 3x from both sides. You have that x minus 3 is equal to negative 9. You add 3 to both sides, and you find that x is equal to 6. And that was the first one. Second one was a little bit more fun than that. You have, for number 20, you have x over x minus 3 minus 4 is equal to 3 over x minus 3. Nicely enough, they all have the same denominator. So what you will do, just like before, is you will multiply by the common denominator, which is x minus 3. Watch your parentheses, otherwise you will screw this up. So you have x times x minus 3 over x minus 3 That was from the distribution here. Still have the distribution here. So you have minus 4 times x minus 3 is equal to 3 times x minus 3 over x minus 3. Now you cancel what you can. X minus 3 cancels here and here. So you have x minus 4x plus 12 is equal to 3, because these cancel. So now you have negative 3x plus 12 is equal to 3. You subtract 12 from both sides. You have that negative 3x is equal to 9. Negative 9. And you have that x is then equal to negative 9 over negative 3. X is equal then to 3. However, there is a problem with that. If x is equal to 3, and I go back to the original, then I am dividing by 0, because this is also one of the zeros of the denominator. And so, because our solution is actually one of the things outside of our domain, we actually say that the solution set is empty. Is empty, or that there is no solution. There is no solution because you have already had the fact that x cannot equal 3, because this is a 0 of the original denominator. Little ethereal, but it is important. Now, let's turn our attention to 21. 21 is a little bit more fun. Not really. In this case, you have x over x plus 2 plus x equals 5x plus 8 over x plus 2. Once again, nicely enough, the denominator is all the same, so you have to distribute x plus 2. In this case, we can already say safely from what we have here is that x cannot equal 2. That's in our negative 2. That's in our domain. Okay? That's a restriction, otherwise the whole thing falls apart. Now, we distribute x plus 2 and x plus 2. Distribute here, distribute here. So, you have x times x plus 2 over x plus 2 plus x times x plus 2, because there's nothing that cancels here, is equal to 5x plus 8 times x plus 2 over x plus 2. And we cancel. X plus, we can go on ahead and distribute this. We have x squared plus 2x is equal to, this cancels this, so we say 5x plus 8. And now we recognize that we're running into a quadratic. Great fun. So, just to make our lives easier, we're going to move everything over to the left, so we're going to subtract 5x from both sides. Well, we can combine like terms, but we'll deal with that in a sec. So, minus 5x here, minus 8 here, minus 8 here. This cancels, this cancels. You have then 0 on the right. I know I skipped a step, but that's okay. I think you all can handle it. X plus 2x is 3x. 3x minus 5x is negative 2x. Still have the negative 8, and still have the x squared. Because this x plus this 2x is 3x, and then you subtract 5x. Okay. Now, that being said, you are looking for the factors of negative 8 that have a difference of negative 2. You know that this is actually going to be x and x. You know that this is going to be 4 and 2. You know the 4 is going to be negative, and the 2 is going to be positive. That tells you then that the zeros is that x is equal to negative 2 and that the x is equal to positive 4. However, as we established earlier by looking at our domain, because having a negative 2 would result in division by 0, we eliminate it from consideration. So the only feasible option is that x is equal to 4. And so that was actually pretty tricky. And that concludes the second part.